Hello everyone and welcome to today's lecture. So today I'd like to go over a few different applications of Fourier series. Specifically, I'll talk about the energy of a signal. I'll also talk about ODEs and PDEs. Specifically for ODEs, we're going to talk about applying Fourier series to the analysis of the solutions to nth order linear constant coefficient ODEs that are inhomogeneous, and for PDEs we'll discuss what are called separable PDEs. And in both scenarios, these are also linear. But in both scenarios, the theory of Fourier series becomes very, very, very useful in terms of solving the actual ordinary differential equation or partial differential equation. But let's start with the first application, which is the energy of a signal. And this application is really just, it hinges on the fact that we have this nice Parseval's inequality that we can write down. So we know that if f of x is some periodic function or periodic signal, with a period of L and its Fourier series converges uniformly, that Parseval's equality says that 2 over L times the integral from negative L over 2 to L over 2 over one period of the function squared will be equal to a naught squared over 2 plus the infinite summation from n equals 1 to infinity of an squared plus bn squared. And we can define this right here as the total energy of the signal f of x. And what's really nice about this is that if this integral right here is the total energy, or 2 over L times this integral is the total energy, what this is saying is that we can split this up into a partial sum plus some remainder term where the total energy of a given signal is from Parseval's equality exactly equal to the energy captured by the first n terms of the Fourier series plus some remainder. And the idea is that the closer E of n is to the total energy, the closer the Fourier series will be to representing the actual function f of x. This is such a nice idea because if we divide both sides of this by the total energy E, you get that the ratio E of n over the total energy is going to be some fractional value, we'll call it P, which gives you an exact measure of how much energy or what percentage of energy is captured by the first n terms in the Fourier series. So for example, if you want to guarantee that 95% of the actual signal's energy is captured by in a given Fourier series expansion, you are going to have to solve for the capital N value such that E of n over E is equal to 0.95. Or greater than or equal to 0.95, we'll say. So what we'll do is we'll look at the relatively simple example from last lecture where we compared the Fourier cosine series to the Fourier sine series of the function f of x is equal to x, where x in the interval from 0 to 1. And on this interval, this function looks like this. And you'll remember that the cosine series converges to the even extension of this function. On this interval. And the sine series converges to the odd extension of this function on this interval. Now, so to denote the cosine series, what that converges to in blue, and what the sine series converges to in red. And you'll remember from that lecture that because the even extension of this function has nicer smoothness properties than the odd extension of the sine series, the Fourier cosine series converges faster, an order of magnitude faster than the Fourier sine series for this example. You recall that the even Fourier series, the cosine series of this function, converges to the summation n equals 1 to infinity of an cosine of n pi times x and plus a naught over 2 where a naught is 1, an was 2 over n squared pi squared times negative 1 to the n minus 1, and the bn's are 0. And the sine series of the extension for this function, or the odd extension of this function, converges to the summation from n equals 1 to infinity of bn sine of n pi x, where bn was 2 over n pi times negative 1 to the n plus 1. And because it's an odd extension, a naught is 0 and an is also 0. And what this means then is that the total energy contained in the even extension will be 1 squared over 2 plus the infinite summation from 1 to infinity of an squared, and the bn's are 0, and I'll just put a naught squared here, our general formula. And same thing for the odd extension, but for the odd extension, a naught and an are 0. So this is just going to be the sum from n equals 1 to infinity of bn squared. So we know that the Fourier cosine series converges much faster than the Fourier sine series. And this is actually what we see with in regards to the energy. So if you were to solve the energy problem, you'd get a much faster convergence and a much faster, the cosine series will converge to the true energy much faster than the cosine series. For both series, the energy, the total energy, E, which is 2 over L times the integral from negative L over 2 to positive L over 2 of f of the extension of x squared. This will reduce to just 2 times the integral from 0 to 1 of x squared dx, which will end up being 2/3. So the energy contained in each of these signals, both the even and the odd extension, is 2/3. So let's take a look at this example from before. And remember, the Fourier sine series is converging much slower than the Fourier cosine series. But if we go here and just visualize first what we're looking at. So I'm going to put a line at 2/3. This axis is the energy axis, and this axis right here is the n axis. And we have we're going to be plotting here a comparison of the cosine series energy and how it changes for various values of n, along with the sine series energy and how that changes for various values of n. So first off, we look at the cosine series. We see that even if there's no frequencies, or no harmonics included, or just the 0th harmonic is included, we're already very, very close to the actual energy of the signal. And just if we include one harmonic, we're essentially on top of the actual energy. This is what we see very, very nicely as the Fourier series converging very, very quickly, the cosine series converging very, very quickly. And as we increase terms here, we only start to get closer and closer and closer to the actual value of the total energy contained in the signal. On the other hand, if we look at the sine series, it's here in these orange dots, the sine series terms only start at the first harmonic, with a B1. And even if you just take one harmonic, it's not even very, very close to the actual energy. B1 squared is right here, which is a little bit more than half of the actual total energy contained in the signal. In addition to that, this takes a lot longer to get to the total energy. So this is the total energy, or I should say that the first two terms of the series. This is the first three terms, the first four terms, and so on and so forth. So you see that it's taken a very, very long time for us to recapture even slightly, the total energy contained in the signal itself. So this is a very, very cool example application right here. And this is very, very important sometimes when it comes to choosing whether you want to do a cosine or a sine expansion. In certain cases for certain functions, depending on how smooth the function is, a cosine series might be better to use, and in other applications a sine series might be better to use. But this is a very neat application and example, I think. And the next main application we want to move into is that of analyzing constant coefficient ordinary differential equations. And to do this, we'll consider a couple different examples. The first example will be a forced mass spring system. And so we'll consider some fixed point, a wall, with a linear spring attached to a mass m. And let's say that the spring has an equilibrium here, and we measure the displacement of the spring y as a function of t. Make the following assumptions. regarding the motion. The first one, we'll assume that the spring is a linear spring. Which means it follows what's called Hooke's law, where the force of the spring is negative k times the displacement of the spring y. Assume that we have a linear friction term, which means that the force of friction will be some constant of proportionality c times the speed, or the velocity, I should say, of the mass as it moves back and forth, which is the force of friction will always point in the direction opposite the velocity and be proportional to the velocity at any point. And lastly, we'll assume that we have some forcing function capital F of t. And if we go through and apply Newton's laws, Newton's second law says that the mass times the acceleration is equal to the net force, the sum of all of the forces on the mass, which will be the force of friction plus the spring restoring force. Oh, and this should be y double dot right here. Plus the forcing function, which is the external force acting on the spring, whatever that will be. Which can be rewritten as my dot plus c times y dot plus k times y is equal to f of t, which, as long as the mass is constant, the spring stiffness is constant, and the friction constant, the friction coefficient, is constant. This is a second order linear constant coefficient inhomogeneous ordinary differential equation. And we're going to analyze these in general a little bit later on using Fourier series. So I want to give you another example, which is chosen based on its very, very close similarity to the mass spring system, but very, very far difference from the mass spring system in terms of where the differential equation comes from. If you consider a circuit, a battery pumping out a voltage of E of t, or E as a function of t, through a circuit with a resistor of resistance R, and inductor of inductance L, and a capacitor of capacitance C. This is sometimes called an LCR circuit. where L is the inductance of some inductor, C is the capacitance of the capacitor, and R is the resistance of the resistor. The differential equation that governs the current flow through such a circuit can be obtained using Kirchhoffs laws, Ohm's law, and the law giving you the relating the current for the capacitor and the current for the inductor. But when this is done, you end up getting a second order differential equation. L I dot dot plus R times I dot plus 1 over C times I is equal to the derivative of the voltage being pumped into the circuit as a function of time. And I always thought that it's remarkable that this is essentially the same second order linear constant coefficient differential equation as obtained for the mass spring system. Where you can think of the inductance of the inductor in the circuit as the mass, the resistance of the resistor in the circuit as the friction coefficient for the linear air resistance, or the linear friction on the mass, and then 1 over C you can think of is essentially the same thing as the stiffness K in the spring equation. And f of t is just the derivative of e of t. But the idea is that qualitatively speaking, these two ordinary differential equations are solved in the exact same way, even though they describe completely different physical systems. So I think this is very neat. And we will focus on systems like these two. I just want to give one more example, to give a third example of where you see what we're about to study in engineering, and that's the example of the beam equation. And this is the equation describing for a general beam how the beam is going to deflect under a load W of x. So if you put a load W of x on the beam, where this is the x-axis, the load could be a function of x. The beam equation describes, this is a fourth order ODE, which describes the deflection of the beam. This is at the second derivative with respect to x of E times I times, we'll call it deflection of the beam, y of x. it's e times I times the second derivative of y with respect to x is equal to this function w of x. This is a fourth order linear inhomogeneous ODE. And in general, E is called the elastic modulus of the material. And I is called the second moment of area of the beam cross section, which in general both of these can be functions of x, but in the case that E and I are constant, you get that this differential equation also reduces to a fourth order constant coefficient inhomogeneous equation. Which is very neat. So what we're going to do is we're going to write down in general what an ODE of this form is going to look like, and discuss how we can use Fourier series to investigate the solutions of such an ODE. So an ODE of the form am dy dt m derivative plus am minus 1 times the m minus first derivative of y with respect to t and all the way down to a1 times the first derivative of y with respect to t plus a naught is equal to some function f of t where a naught through am are real numbers, constant real numbers, is called an nth order linear constant coefficient ordinary differential equation. And these should be familiar with you from your undergraduate ordinary differential equations class. We'll call a differential equation of this form star in our future calculations. we also might adopt a slightly nicer notation. We'll denote this entire left-hand side as L of y. And note that it's important to go through and check, but L of y is a linear operator on functions. For instance, if you were to take L of alpha y plus beta alpha y1 plus beta y2 for two separate functions, y1 and y2, this is going to be the same thing as alpha times L of y1 plus beta times L of y2. This will be important a little bit later on. And this is one of the defining characteristics of having a linear ordinary differential equation. But you'll hopefully remember from your undergraduate differential equations course that the general solution of star is found by solving for the general solution of the homogeneous form of star, which we call star H, which is the problem L of y is equal to 0. This is step 1. And then solving for a particular solution to the inhomogeneous problem. Which typically involves either a variation of constants or the method of undetermined coefficients. The solution to the homogeneous problem is typically called YH, and the solution for the particular solution is sometimes called YP. But once YH and YP are found, then the general solution to star is just the sum of both. So y of t will be equal to YH of t plus YP of t. Where this is the homogeneous, or the general solution to the homogeneous problem. and this is a particular solution. To star. And you can verify this relatively easily. If you look at L of y, this is the same thing as L of yh plus yp, which is L of yh plus L of yp, due to the linearity of the differential operator, and because yh satisfies the homogeneous equation, the general solution to this will be 0, and this will just be the forcing function. So this definitely satisfies L of y. In the typical ODEs course, you show that this is the correct form for the general solution. And one of the things that this general solution, right, and specifically the homogeneous solution, depends on are the roots of the characteristic polynomial of this equation itself. The characteristic polynomial for this differential equation right here. This is the nth order polynomial, Pm of lambda, which is am times lambda to the mth power plus am minus 1 times lambda to the m minus 1 plus a1 times lambda plus a naught. The roots of the characteristic polynomial are called eigenvalues, because they're actually the eigenvalues of a specific matrix. If you were to rewrite this mth order ODE as a system of m first order ordinary differential equations, the eigenvalues of the matrix that you get would be the same as the roots of this characteristic polynomial. But these eigenvalues actually determine the behavior of the solutions to this differential equation. In a very fundamental way. You say that if the eigenvalues of the system, which is the roots of the characteristic polynomial, are all, or I should say all have a negative real part, then the solution to star is globally asymptotically stable. And this means that the limit as t goes to 0 of yh of t will be equal to 0. If all the eigenvalues of A with 0 real part are simple or have multiplicity 1, the solution is stable. If the eigenvalues of star, I should say, if an eigenvalue I should say very clearly, if any eigenvalue has positive real part, the solution to star is unstable. And we're going to focus on, in this lecture, on the case of global asymptotic stability, because I think this is really where a lot of the interesting dynamics happen. And you can go through and verify that for positive values, say in the first or second example of M, C, K, or of L, R, and C, that you have this case of global asymptotic stability. This is also why the solution in the general form here, the homogeneous solution, is sometimes called the transient solution. So YH here is sometimes called the transient solution because in the case of global asymptotic stability, so in the case of negative real parts for all of the eigenvalues, this YH goes to 0. Right? So in case 1 from before, YH of t goes to 0 or dies out as time gets larger and larger and larger. So what's left over is just the important thing, which is the particular solution, which is sometimes called the steady state solution in the case that YH goes to 0. Now we'll consider the case of a periodic forcing function. Over the forcing function on the right hand side of the differential equation is periodic. So recall that if the input f of t is periodic, with period L equal to 2 pi over omega, where omega is the driving frequency, of the input it can be represented as a Fourier series expansion sum from negative infinity. We're going to use the special form for the Fourier series expansion in terms of the exponential, just to not have to rewrite too many ANs and BNs. Cn times e to the I n omega times t. Recall here that if you were to plug in, you can directly get this back in terms of ANs and BNs, as well as this omega right here. Omega is equal to 2 pi over L. Right, so this is a little bit of a simpler way of kind of thinking about f of t and the driving frequency. But you could very easily convert this back to the standard Fourier series representation. We're just going to use this because it's a little bit easier to write down and manipulate mathematically. And to find the output, of the signal, xp of t let us look for Fourier series expansion for xp of t, also in a Fourier series expansion. Remember that the general solution to the differential equation, and I should not use x here, I want to use y here. The general solution to our differential equation is yh plus yp. And as t goes to infinity, we're dealing with the case of asymptotic stability. We're assuming the eigenvalues are, the real parts of the eigenvalues are negative, so yh goes to 0. The transient goes to 0 as t goes to infinity. So if this is the case, then we can look for yp in this form and see how it's related to the input to the problem, which is f of t. So if we plug both expansions or here, both expressions into the differential equation, which is L of y, L of yp is equal to f of t, or more specifically, a m times the nth derivative of yp d tm plus a m minus 1 times the nth derivative, m minus first derivative of yp with respect to t plus all the way down to a1, the first derivative of yp with respect to t, plus a naught times y p this would be equal to f of t and for any n, if I take the nth derivative here, or the nth, so the kth derivative of yp, is going to be the summation from n equal negative infinity to infinity of dn times I n omega to the k times e to the I times n omega t. So if I plug the Fourier series expansion for both of these expressions in on the left hand side, I'm going to get the expression at the summation from m equals negative infinity to infinity of am times I n omega to the m plus am minus 1 times I n omega to the m minus 1 plus all the way down to a1 times I n omega plus a naught all times e to the I n omega t times dn this is the left-hand side of the differential equation when we plug yp into the left-hand side of the differential equation, and this has to be equal to the right-hand side, which has a Fourier series expansion of this. Which gives us, if you notice here, you think about what this is for a second, this left-hand side is just saying that this is the characteristic polynomial Pm of I times n times omega times dn times e to the I n omega t, and this has to be equal to this infinite sum right here. Remember, so now this is the Fourier series expansion of L O Y P, and this is the Fourier series expansion of f of t, the forcing function. And in order for these two things to be equal and satisfy the differential equation, we then have to have the characteristic polynomial evaluated at I n omega times dn has to be equal to Cn. for every n in the integers. Which means that dn must be equal to Cn over a characteristic polynomial evaluated at I times n times omega. Where Pm of I and omega is never 0 because we are assuming that the solution is asymptotically stable. So we never have purely complex roots to this characteristic polynomial if we're dealing with the case of asymptotic stability. All the eigenvalues have a negative real part. Things become a little bit more complicated in other scenarios, but we're just going to focus on this simple scenario right here. Important thing to note here, the function ym of s, which is 1 over p, the characteristic polynomial at s, is called the transfer function. I should say sometimes called in certain literature. And the function ym of I omega, the function of omega, is called the frequency response function. Because it's giving us a direct relationship between the Fourier series coefficients of an impulse forcing function, which are these Cn's right here, and the solution dn, right, the behavior of this function ym of I times n omega times Cn is telling you directly how the Fourier coefficients of the solution, the particular solution, respond, right, to a change in frequency or change in the C value right here, with this with n right here as well. So for different values of n and different values of omega. And the solution of our system for the particular solution, xp of t or yp of t, is exactly equal to this will make this a little more clear, the sum from negative infinity to infinity of Cn times ym of I and omega times e to the I n omega t. So what this is saying is that directly, if we can go through and find the Fourier series of our forcing function, the right-hand side of the differential equation, we can go through and directly find the particular solution to this ODE system, which is very, very cool. And this is after, this is valid after the transition period through which the transient goes to 0. This solution is sometimes called this is why it's sometimes called the steady state solution. In the case of asymptotic stability. And I have one final remark here on the convergence, right? Whether this is going to converge or not, and we can actually say for certain some very, very nice things on the convergence surrounding this Fourier series for yp. Since frequency response function ym of I times m omega is on the order of 1 over n to the m, since ym of n omega, this frequency response function, is 1 over the characteristic polynomial. This is going to be a polynomial on the order of n to the m. So since ym of I n omega is a polynomial and it's on the order of n to the m, the Fourier series of our solution right here is actually faster than the Fourier series for the input. Specifically, the Fourier series coefficients Bn is ym of I n omega times Cn and if the Fourier series for the input is on the order of 1 over n to the p, actually will be 1 over n to the k, then Bn is going to be on the order of 1 over n to the m times 1 over n to the k, or 1 over, on the order of 1 over to the n to the m plus k. So this Fourier series is actually going to converge faster than the input, which is very, very neat. And a good exercise would be to prove that because Bn is ym of I n omega, and B negative n is ym of negative I n omega. These two values are actually complex conjugates of one another. So just like for the Fourier series expansion in this exponential form of the input, right, where these the complex parts end up canceling one another, and it's very nice, very nicely for this input. This is going to be a real valued sum, which is equivalent to the an and bn notation. The exact same thing happens for this Fourier series right here. It's a very good exercise to go through and prove that and show that for yourself. But this is everything that I wanted to talk about for applying the Fourier series to a constant coefficient nth order differential equation. And I think that it's very clear now how to approach problems, any problem of this form.